All right, class. Hope you had a good Thanksgiving break. Now we're going to talk about radioactivity. And first, we're going to talk a little bit about the nucleus. Let's go ahead and take notes. So, review. Protons and neutrons are in the nucleus, remember? The nucleus is a heavy, relatively heavy ball of protons and neutrons in the middle. Neutrons help dilute, diffuse the positive charge off the protons. So you got this proton that has a lot of positive charge. You got to have some type of neutral buffer in there to keep the nucleus stable. And now remember that the protons give you positive charge, and it identifies the number of protons identify the element. The mass is attributed to both the protons and neutrons. So to keep things stable, nuclear force is the force that holds the protons and neutrons together, and we can actually calculate this. And how to calculate that is by taking the actual atomic mass and then subtracting from that the sum of the mass of protons and neutrons. And actually should be, you take the mass of the protons and neutrons, if you got, and we'll show you how to do this. And you got this big number, and you subtract the actual mass, you're going to get the difference. And this difference can be, using Einstein's equation, can be used to calculate how much the energy it takes to make this nuclear force. And so the actual mass of the protons and neutrons and electrons are listed here. Now, instead of AMU, we're using Daltons, and a proton is 1.0073. Neutrons are 1.0087, so they're a little bit larger than the protons, a little bit heavier. And the electrons are basically 5.49 times 10 to the minus 3 Daltons, and they're very, very small. And hence, you'd see the difference in masses. And so we're going to use this and figure out the binding energy or the energy used in the nuclear force for each atom. And so what we have is we have boron 10. Here's my example. It has a mass of 10.012937 Daltons. And boron 10 has 5 protons and 5 neutrons. And so there are several isotopes of boron. There's boron 11, boron 9, but we're just looking at boron 10 in particular. And we can actually measure how much mass these things have, each of these elements. We don't care about electrons at this point. And for the light elements, everything below, say, uranium 93, the mass of electrons do not matter in calculating the binding energy. And so we're going to use E equals mc squared to figure out the difference in mass to determine the binding energy. And 1 Dalton is related to 1.6605 times 10 to the minus 27 kilograms. So let's go ahead and work on this. So let me get my pen. Oh, red's good. Let's go ahead and stick with red. So we've got 5 protons. So each one is 1.0073. I'm going to multiply that by 5. And I'm going to do the calculation with me. 1.0073 times 5 is going to be 5.0365 Daltons. We've got 5 neutrons. So 1.0087 times 5 gives me, and I'm going to that's going to give me 5.0435 Daltons. And so when I add that together, 5.0365 plus 5.0435, I'm going to get 10.0800 Daltons. So that's the mass it should be. The actual mass is up here, 10.0129 And 3, 7, let's just go ahead into 9 and subtract that from the 10.08. And I'm going to get 0.0671 Daltons. And this is called the mass defect or mass defect. So this mass is used by the atom to create binding energy, which helps supply the nuclear force to keep this together. So using E is equal to mc squared, we know E, that's the binding energy, is equal to the mass. Well, the mass is 0.0671, but it can't be in Daltons, we have to be in kilograms. So we're going to multiply this by 1.6605 times 10 to the minus 27. And this mass now is equal to 1.114 times 10 to the minus 28 kilograms. So we'll put that up here, 1.114 times 10 to the minus 28 times C, which is 2.98, speed of light, times 10 to the 8th. And we're going to square that. And so our binding energy is going to be there's going to be 9.89 times 10 to the minus 12 joules. And that's the binding energy per atom. So the energy looks small. Let me rewrite this. Binding energy is 9.89 times 10 to the minus 12 joules. It looks small, it looks minute, but if you got a mole of these, energy becomes quite large. So this is for one atom, and it's actually pretty significant when you think about it. So when we talk about energies, we've got 3 types: kinetic, which is movement. We got binding, this is the nuclear energy for the nuclear force. And then potential, this is a form of electrostatic repulsion. Remember, you got positive in the middle, you got electrons flying around, so here's your potential energy. Now, some elements have unstable nucleus. And the atoms of that have different masses of the same element can be stable or unstable. Why? Because you either have too many protons or too many neutrons, or both, and for some reason the nucleus can't handle. There's not enough force developed to keep them constant, and then they break apart. And this is where we come with natural radiation. It comes from the natural decay of elements. And it's basically this decay is breaking down of matter, and we're going to get different elements being formed. And then we call these things radioisotopes. And what we have is that we have the stable elements. Most elements with less than 20 protons has a stability ratio, have a neutron-proton ratio of 1:1. If you get between 20 and 82 protons, the ratio increases 1.5 neutrons to protons. So neutrons here, protons here, you're going to get this curve that looks going like this. After 83, all the elements are radioactive. We haven't found anything stable yet. There is thought that some of the higher elements going towards the noble gases, say about 118, 117, will be close to, should not be radioactive, but we don't know that yet. We hypothesize that, but we haven't had enough information yet to see if those things are radioactive or not. Now, when we talk about natural decay, we have 4 that we're going to look at. Actually, there's 5. The last one I forgot to put on this slide, but it's electron capture. So alpha is also called a helium nucleus. For helium for two neutrons, 2 protons, 2 neutrons for a mass of 4, and this thing flies out. This is very, very small. Beta is actually an electron. And positron, we realized about 50 years ago, that's what we call antimatter. It's actually opposite of an electron, and we call it a positron. It has the same identical mass of an electron, but it's positively charged. So that's an opposite charge of the electron. We'll call this positron. Gamma radiation is basically electromagnetic radiation. High frequency light. Have very high energy, and this thing can break bonds if it comes in contact with the human body or any type of organic compound. And this comes from when the atom relaxes or loses energy because it's too unstable. And sometimes you get it when you have a positron react with an electron, annihilate each other like antimatter will do, and you get this burst of radiation. This is why positron emission was very hard to figure out. Last, electron capture is when the electron is captured by the nucleus. It happens only on occasion, and it's when the probability is just right for that to happen. Now, well, we have alpha decay because we have too many protons and neutrons in the nucleus. And to get it stable, it ejects an helium nucleus, and then it tries to become more stable. Sometimes it does, sometimes it doesn't. Beta decay has too many neutrons. The neutron will break apart to form a positron, a proton plus a high energy electron. So a neutron will break apart for a proton and an electron. Positron, not too many protons, so the proton will break apart to form a neutron plus an electron. And we get this, actually it's a positron, and this positron will come out. And this is what these decays are. So next week we'll show you how to balance nuclear reaction equations. But for this week you're going to be tackling how to determine binding energy in atoms.